All right, so put these in your notes. If you have it, then it'll be harder. That's just your choice. All right. So this is the finale of this chapter. It's manageable. And honestly, none of this itself is difficult. It's just a lot of steps. If we work through it in a very systematic way, you'll be fine. And to me, 80% of this is really pretty easy. 20% of it makes it a little bit more difficult, but you can do it. I don't know. Usually by now, this isn't that bad. So in solution stoichiometry, what we're doing, if you watch the video, you'll think this is some repeat, but we're going to add two solutions together. All right, one's going to pour into there. When they react, they'll form some sort of precipitate. That will be in the bottom. It is important that the precipitate is not in the solution anymore. Solutions are things that are aqueous, that are dissolved. Now, it's in the beaker, but it's at the bottom of the beaker. It is not dissolved and hanging out in it. So anything in the precipitate is not in the solution anymore. All right, so we'll have a precipitate. We'll have some spectator ions. There'll be two of those, and we'll have an excess ion. There's typically just one of those. Okay? In these problems, our job is to find the concentration. That's supposed to be a bracket, and remember, there's two of them. We're going to find the concentration, one of those, and then we're going to find the mass of the precipitate. Those are what we're looking for. You all right with that? Now, we will also ask you what the concentration of the reactant is that's in the limiting reactant and the precipitate. And hopefully you recall from the videos that the concentration of that is always 0. The reason why the concentration of the limiting reactant and precipitate is 0 is because 100% of it is tied to the solid. And please remember, the solid is not dissolved. It's a precipitate. It is not aqueous at all. So if there are no ions in the solution, then it has no concentration. All right. So, and PPT, precipitate. Yeah, limiting reactant and precipitate. All right. Now, having said that, we're going to dive right in and start working on a problem. These problems typically take a lot of room. So I wouldn't start one unless you have at least 5 inches left on your paper. I would turn over to the next page. Now, that's up to you, but that's my recommendation. All right, so this one of you in your feedback asked me to start with things that were easy and work till they're hard. I feel like I always do that, but I focused on making sure I started with an easier one, and we'll work our way up with difficulty. So we're just going to follow the steps I just had you write down to do this. So we have this problem. The first step says to do what? Balance. So silver nitrate is AgNO3 plus sodium chloride, NaCl. It forms AgCl plus NaNO3. I had a student in my first hour ask me how you know what things are made on the right side. That's chapter 2. That's chapter 3. It is time that you know how to complete the right side of the equation. This is a double reaction, or double replacement reaction. We've done that in this chapter as well. The metals just change places. All right. This problem is very easy to balance because they're all ones. That will make a lot of this problem significantly easier. Okay. What's the next step say to do? Determine the precipitate. Now, it's time in your chemistry life that you should be able to do this as well. Now, you don't have a list given to you in this problem, but for this problem, I'm hoping you know at least one thing, and that is that NO3 never makes a precipitate. So it must be over here. It can't be what's hanging out with NO3, so it must be this. AgCl will be my precipitate. Which means these two things are called what? Spectator ions. Okay. What does the next step say to do? Determine the limiting reactant. Now, it gave you two options. One is the option from last unit. Use the given moles to solve for grams of the precipitate. You can certainly do that, and that is acceptable. If you really like that way, then keep doing it that way. In this unit, I'm going to look at the moles and just use their coefficients to figure things out. So, what I mean by that is we find their moles. Now, this problem is supposed to be easier. One of the reasons it's easier is because I just gave you the moles. So I have 0.05 moles here. How many moles do I have here? 0.2 moles here. I did forget, by the way, in this problem, I forgot I needed to give you the total volume in the problem, which I did not. So let's just say it has 8.8 liters. Okay, you need that to be able to solve these problems. I just forgot to type it in. All right. Okay, so back to determining the limiting reactant. If we are in moles, it's pretty simple if these are both ones, because I need the same amount of each. So which one will be the limiting reactant then? All right, AgNO3, because it's the smaller number of the two. If they're in moles, and it's a 1-to-1 ratio, then yes, it is always that easy. Yeah, you would do this. So now we're going to pretend, so don't put what I'm putting right now. Let's pretend this was a 2 right here. And look at the screen for a minute. We would look at this number, and then we would say the following question. Is this value at least 2 times bigger than that value? That's how we would ask ourselves. If the answer was no, then this would be the limiting reactant. If the answer was yes, then the other thing would. Let me say that question one more time out loud and see if it clicks. You ready? So you find the one with the largest coefficient, and you say, is this number at least 2 times bigger than that number? Once again, this answer would be no, so that would be the limiting reactant. Does that make sense? What's that? All right, because for this reaction to happen, now this is fake land, but if it was a 2 and 1, every time one of these reacted, it needed 2 of those to react. Heather. All right, let's undo it then, and we'll talk it through that way. And we will do most of these. You will have to do this process, so this is good. All right, we will pretend this is a 2, correct? We now would say, because we go to the higher coefficient, we would say, is this number at least 2 times bigger than that number? What's the answer to that question? Yes. So that would make this still the limiting reactant. Two times 0.2? Yeah, that's the same thing I'm saying. Okay, that's fine. Last hour, a kid did the same thing, and what he said made more sense. I didn't even think he was speaking English. What you just said does make sense. But the other one, I'm like, sure, you go with that. I didn't even know what you just said. All right, let's get rid of this. All right, so now we have our limiting reactant is right here, correct? Oh, that was terrible. Our precipitate is right here. It's important that we know where both of those are. Now, please look. Since, I'm going to erase this in a second, but since AgNO3, since there's like one Ag and one NO3, you all right with this so far? The concentration of Ag plus and the concentration of NO3 minus will just be equal to whatever you were given here. But if, let's pretend there was a 2, then this would still be 1, but this would be 2 times the concentration of whatever you had here. Okay? We're going to run into those problems in a minute too. And if that didn't make sense, that's fine yet, because we're going to do another problem. Okay, so we have determined limiting reactant. We've determined the precipitate. We have the moles. So what's the next step it asks me to do? All right, awesome. It asks me to determine the grams of my precipitate. So I'm looking for grams of AgCl. All right. Now, please remember, from all of our lovely limiting reactant problems, yes? You don't? Locks? On the iPads? Yeah. Starts with a 9. Okay, I'll come over in a second. Okay. Got you. All right. We ready? So make sure you're with me on this. It's not too bad. You take your limiting reactant. Whenever we do a picket fence with these things, we always start with the limiting reactant. And here's the nice thing. There's only one total picket fence in these problems. If you use that first process to determine your limiting reactant. Okay, so I have 0.05 moles of AgNO3. The picket fence at least always tells me what the bottom of the next thing is, right? And that would be moles AgNO3. And where do I find the number that goes with that? Oh, it's not moles per liter. It's the coefficient. All right, for every 1 mole of AgNO3, how many moles of AgCl do I have? 1 mole AgCl. What must come down here then? Mole AgCl, and that's for every 1, and then 143 grams. Now, tell your lab partner where I got that number. It's just from the things, right? Okay. So coming back, what was that post? 7.15. Now, it would behoove you all to have a calculator today. If you don't have one, I have some loaners, ones that are right behind this cabinet right here. They're pretty nice ones. There you go. All right. So 7.15 grams of AgCl. Okay, so you should have written a note to yourself when it said, determine the mass of the precipitate by starting with the moles of the limiting reactant. Wasn't that step? That's what we just did. So far, are we okay? I don't expect by the end of the day for you to be perfect at these, but at least hopefully you can feel a little bit better about them than you started the day. After we found the mass of our precipitate, what was the next step? All right, find the concentration of each ion. So let's reason through this. I'm going to come back here. First off, in A, please look. The concentration of the ion in both the limiting reactant and precipitate, this is stupid, this shouldn't say grams, by the way. It should be a capital M, is 0 molar. All right, so looking up here in your notes, I boxed the limiting reactant and the precipitate. Which thing is in both? Ag. So the concentration of Ag is equal to what? 0. It is completely consumed and it's completely locked into the precipitate at the bottom, which once again means it's not in the solution. The ion is not an ion, it's stuck to the precipitate. Okay. So that one, not too hard. If you know the limiting reactant, and you're ready to roll. Okay, the next problem, piece of instruction, says to find the concentration of your spectator ions, right? So what are my spectator ions? All right, Na plus and NO3 minus. Okay, we solved for both of these in the exact same way. They're not the same answer, though. Those are terrible, but whatever. Okay, so no, it's not a picket fence, Tom. What are you doing? You don't need the vertical lines there. We're just dividing. I'm sorry. It's just Pavlovian response to write a line and put a vertical line on it. Right. All right, so when we're finding molarity, we're finding moles per liter, right? So I just need to know from the start, how many moles of Na plus did I have? That was the 0.2. Sorry, just had them backwards. 0.2, right? All right, what's the total volume? That's why I had to add it. It was 0.8. So we end up with 0.25 molar. That's the concentration of the Na. Remember, a spectator ion's concentration at the end is exactly the same as its concentration at the beginning. All right, now NO3, the denominator is still the same. We're going to use this actually in 3 consecutive steps. All right, what was my initial of, this is the NO3. That was the 0.05, right? All right, 0.05 divided by 0.8. I can't do that one in my head. This number here is moles. Is that what you're asking? Yeah. Yep, thank you. I should have not been lazy. All right. So for me, we're 80% of the way there, and I don't think this is that bad. Like it takes a lot of time. I mean, we're 20 minutes into the hour, and we haven't even finished the first problem. But it's doable. The final step is the only one that is probably a little bit tricky. We're going to take the excess reactant and find its concentration. And that was Cl minus, wasn't it? Yeah. Okay. So, it's the same as we did last unit. To find the excess, you take your initial minus your used and divide it by your new volume, which is 0.8 liters. Now, since the coefficients are 1 to 1, this is actually very simple. The initial was 0.2, correct? And please look up here. Follow this logic. The amount of this used up is determined by your limiting reactant, right? Since your limiting reactant and your excess are in a 1-to-1 ratio, the amount you use of excess is equal to the amount of limiting that you had. So, my initial was 0.2. My used was how much limiting reactant I had, 0.05. So I end up with 0.15 divided by 0.8. Okay, 0.1875 molar, or moles per liter. All right, what did you think on this? Will you tell your lab partner for 1 minute what you understood and what you did not? Ready, go. Okay, with balancing the reaction. Okay. Determining the precipitate using solubility rules. That's not a ton of you. You will have the chart. But remember, if it has NO3 or acetate, it's not going to form precipitate. How many were okay at looking at the limiting reactant and determining that? Raise your hands. Okay, that one was all right. Mass of the precipitate. If you're okay with that, raise your hand. Okay. How many were okay with this part? If it's a limiting and the precipitate is 0. Yeah, thank you, Newman. I agree. That's the easiest part. Okay, spectator ions. If you're okay with that, raise your hands. Okay. And then this one, raise your hands. Okay, good. Most of you are raising your hands for every one, so that's a good sign. Remember those good feelings as we work through this next one. Okay. This next one, well, first, let me go back just a second here. This problem was made easier for a couple of reasons. These ones right here made it a lot easier, right? All right. The other thing, I gave you the moles. So you didn't have to calculate those. From now on you will, but that's not that hard. The main thing that you would never really know yet that made this easy is there were no subscripts, like a 2. If there's a subscript, things get a little bit more difficult, and that's coming to town here on these next ones. So we'll do it. Just be patient. We're just going to follow the same steps, and we'll be all right. So aluminum nitrate is added to sodium hydroxide. I'll write that out for you. Sorry. Okay, I'll help you balance it. All right, so far where you wrote and balanced it, the next step is to determine the precipitate, correct? All right, the precipitate will never have what thing in it? NO3. So it must be this one, which is your solid, which it is. All right, which means these must be your spectator ions. We okay with that? Good. All right, the next step is to determine your limiting reactant. Now, in order to do that, you must convert everything into moles, and then you can do your math. So Please look at the screen with me. We did this for like 1 minute yesterday, so I don't expect you to have it yet, but please make sure you have it now. So 300 milliliters really needs to be 0.3 liters. Are you okay with that? 100 milliliters needs to be 0.1 liter. Okay. To find the moles, you take the liters times the molarity. The liters will cancel out, and you're left with just moles. So I have 0.3 times 0.6. And that's 0.18. So in this new beaker, well, I guess this is before I've added them, I have 0.18 moles of AlNO33. I come over and I do the same thing with NaOH. I take 0.1, that was my volume in liters, I multiply it by my molarity, which is 0.4. And I get 0.04 moles of NaOH. Okay, go ahead and write those in, and then when you have that, look at the screen. Yes, a capital M means moles over liters. Well, really, if you've watched, I never have once just written a lowercase m. I always write it out. There is, the abbreviation for moles is MOL. And I never abbreviate it because I'm already there. I mean, it's not that much harder for me to write an E. The little m, there's too many things that an m is, so they don't abbreviate moles. All right. Now, you may in your notes, and that's fine as long as you know what you're doing. Okay, now, look. This is a 1, and this is a 3. So it is a little harder. This one is obvious to your eyes, so it's not that hard, but let's walk through this question. We find the higher coefficient, and we find the moles. And we ask, is this number at least 3 times larger than that number? What's the answer to that question? No. It is a no, which means what is my limiting reactant? NaOH. Is everybody okay with that? Okay. That's a pretty simple process as long as one of the coefficients is a 1. If it's like a 2 and a 3, you do have to multiply them by the 2 and the 3 and see which one's the smaller number. All right. So here we go. We now know, let me get rid of some of this. Get rid of that. We know this is my limiting reactant, right? So limiting reactant, precipitate. Okay. The next thing to do is to find the mass of the precipitate, correct? All right. In order to do that, I start with moles. Which moles? All right, the moles of the limiting reactant. 0.04 moles what must come down on the bottom then? This time it's a 3 mole NaOH. I'm solving for grams of AlOH3, so that must be the one on top, and there is a 1. So I must have a 1 mole AlOH3 on the bottom. And then what do I need on the top? I need the mass of that. Wow, that was weird. You're like a ninja. All right. I think it's 79. Someone check me. You what? Are you lost? Okay. I don't want to either. Hey Siri. Oh, she didn't wake up. I think it's 78. Okay, sorry, I thought it was 79. All right, so 78 grams of AlOH3, and then I take 0.4, multiply it by 78, and divide by 3. Yeah, sorry, 0.04. 1.1 what? Okay. So now we're doing it right. Okay? We have to be very good accountants on these next few steps though. All right. So, the next piece, well, the next one's actually the easiest one, right, Newman? We want to find what ion, well, I shouldn't say what ion, what thing is in both the limiting reactant and the precipitate, the hydroxide. So right off, right here, we know the hydroxide concentration is equal to 0. Because it's completely used, because it's limiting, and it's completely tied to the solid at the bottom. It's not in the solution. Okay, so the next, and I like to do them the easy ones first and then the hard ones later. The next is just to find your spectator ion concentration, right? So I'm looking for the concentration of Na again and the concentration of NO3. Now, be really good accountants here. The first thing, the denominator is the same in both. And this actually is probably the number one place kids screw up. You must make sure to add your two volumes. So you had 0.3 liters, but you mixed it with 0.1. So you add them, so your new volume is 0.4 liters. And that'll be the same in all the rest of the steps. Okay, now these are spectator ions, which means the moles of them available has never changed throughout the entire thing, right? So I just need to find how many moles there were in the first place. So please look. We have to be careful here. Is there a subscript with OH in NaOH? No. So the moles of hydroxide are just equal to this. So that one wasn't too bad. So 0.04 divided by 0.4 equals 0.1, right? You all right with that? Raise your hand if you're okay with that. The next one. For every one AlNO3, there are 3 NO3s. Yes. Right here. That was this number times that number forever, a long time ago. Is that good? Awesome, thank you. Okay, so one more time. For every NO3, there are 3 NO3s. I keep saying that, which means the moles of NO3 minus are 3 times greater than the moles of the whole thing. It's made out of 3 pieces. Sorry. So it's an Al with an NO3, an NO3, and an NO3. When these break apart, how many ALs are left? 1. But how many NO3s? 3. And if all of this was 0.18 when it was together, then you must multiply it by 3 to get the concentration. I keep saying that. I'm sorry. The moles of NO3. So I'm going to come back here. That's what I say. You have to be a good accountant. You have to notice every number that matters and every number that doesn't. When I say the one that does it, like this 3, we don't worry about that in these steps. That 3 we really worry about. Okay. So 0.54 is the initial moles of the NO3 ion. All right. I don't know this number. $1.35. Right here? It can't be. 0.18. Well, it is. It's 0.18 times 3. It's 18 times 3 is 54, but you have it 1 decimal. Or 2 decimals, I should say. Okay, now, this is where we ran out of time last hour. We have 10 minutes. That'll be good. This is the tricky part here, and that's the excess reactant. Just to think it through, it's not that bad. The excess reactant is equal to the initial right? Okay, fine. Well, what thing are we talking about here, by the way? We're talking about AG, is that right? Oh, yeah, AL, we're on that problem now. All right, so I come up here. Finding the initial of AL probably isn't that bad. It's just right here, right? Since there's 1 AL, it's just equal to the initial moles of the whole thing. So that part, we're good. So I'm gonna erase this, but just remember that says initial and used. All right, the used here, we come up here, and we really have to be good thinkers here. Notice every one of these we use 3 of those. Do I need to say that again? For every 1 AL we use 3 of these. So this is what we do. We take the amount of our limiting reactant and we divide it by this number. Yep. Because that will tell me how much was used of aluminum. Because remember, the amount of excess used is determined by the amount of limiting reactant. But since it's a 3-to-1 ratio, I had to divide the amount of my limiting reactant by 3. Now, that is the amount used, right? So I'm going to come back here, and I'm going to put that in here. 0.0133. You plug this all in, and I don't have my cheat sheet. It's like 0.42. No? 0.147? Okay, I was way off. Okay, that's what I thought it was. It's 0.41. Pretty sure. That says AL plus 3. That's when you subtracted, but you still have to divide by 0.4. Okay, now we got everything. Yes, ma'am. Yeah, we find the moles of the ions. Oh, ouch. All right. How much fun was that? Really? Okay. So one more time, if you would work through this tonight, we can check it all in the morning and see how we do. We're looking for the exact same thing. The mass of the precipitate, the concentration of everything left, the limiting reactant, all that stuff.